Can you see my screen?
Yes.
Okay. Okay, so you are studying differentiability. So as let me go back here and show you again. So if I started with a curve f from an open interval AB to Rn, and which have this component, and then we say it's differentiable at a point t equal to t naught if this holds, and in this case, say h was in R. All right, the same limit as we did for one real variable. So here, since function has the map f has n component, so this will actually be a tuple of n limits. So this, which means uh, this actually means limit h tends to 0, f1 t naught plus h minus f1 t naught by h, limit h tends to 0, fn t naught plus h minus fn t naught by h. So this tuple of n limits. All right, so let us look at example. So this part perhaps you have seen, right? So this one. So what is the physical representation, physical interpretation of this, right? So if you look at, let's say, gamma from an interval AB, you can put close, doesn't matter. We will not consider endpoint. To, let's say, R3. All right. So gamma has three components: gamma 1t, gamma 2t, gamma 3t. Right. So assume this is, suppose, well, yeah. So example will come there. Before that, let me discuss a little bit here. So this has three component: gamma 1, gamma 2, and gamma 3, and assume this gamma 2 is differentiable. So this then this limit, actually, this limit one calls this limit as f prime t naught, as we did in real variable. So the question is, what is the interpretation of gamma prime t, right? So this bit I call first interpretation. So let us try to draw the picture. So suppose you have some curve. So at each point you have this is suppose this is called gamma t naught, let's say, right? So what we are trying to look at is the following limit, right? Following quotient gamma t naught plus h minus gamma t naught, right? So this is gamma t naught. So suppose let us look at the vector. So this vector is gamma t naught, and suppose this is gamma t naught plus h. Right, so this is the vector, right? And what we wanted is the difference between these two. So we need to look at this. No. Right. So this is the difference, and so we want this gamma t naught plus h minus gamma t naught. So what do you want? This vector, right? So this vector is just gamma t naught plus h minus gamma t naught, right? Is it correct? Yeah. Or you can look at this as this line, and if you look at the quotient, sorry, if you look at the quotient, this is nothing but the slope of this line, right? Slope of this line, right? Now as h tends to 0, as h moves like this, yeah, as h moves this way, h tends to 0, gamma t naught plus h tends to gamma t naught, and this line actually becomes the tangent, right? So this is the vector gamma prime t naught. So limit h tends to 0, which is this gamma prime t naught, is the slope of the tangent of the curve gamma t at t equal to t naught. Is this fine? So this is geometric interpretation, and physical interpretation. So geometric interpretation is this. And physical interpretation so this is the rate of change of the displacement. So this is gamma prime t naught is the velocity which you already know, velocity of particle moving along gamma t along the curve. gamma t. So gamma t is the displacement at time t. Right. So physical interpretation you have already seen. Geometric interpretation you might have seen also. So, so does this make sense?
Sir,
Yes.
I think I'm a little confused. Like in higher dimensions, like in when we are in when we plot the graphs in 2D, that is x x by y. We figure the slope of a line is the angle it makes with the x-axis, right? But how
Right.
do we define the slope of a line in R3?
Right. So the point is that is true. So you don't have slope of a line. Right. That is true. So when you have line in R3, you've got Jackson cosines. So you've got a vector actually,
Hmm.
right? You have got a vector. So the vector, yeah. So the point is this is a little bit of coordinate geometry. So so what is the vector? So this is the vector. Yeah. So consider this gamma prime t. If you consider this to be a vector, well, it would be the some modulus, but it would be along the same direction as this one, right? So as a vector, it will be something like this, right? So so now that actually this question lead us to the notion of tangent line, notion of the tangent line of the curve of the curve gamma. So so this, of course, the tangent line, this, it should pass through, it should touch uh, the curve gamma t at t equal to t naught, and the equation of this would be the equation of the tangent line is, let's say, L t is gamma of t naught plus gamma prime t minus t naught. All right. So so what you so gamma prime t naught, yes, gamma prime t naught into t minus t naught. So so the point is here, you look at the vector gamma prime t, look at the vector gamma prime t is this one, which applies here, and you basically, and this point is gamma t, right? So we shift this, so shift this here, right? And uh, how do you shift such things? It's basically, of course, you have the translation. So we do this translation, but then so you need to look at the equation of this line. So what is the equation of this line? So this is the vector, right? So you can think of this as a line also. So suppose you are given a vector v. So can you get a line?
Uh, the line
Go to
passing
origin.
through ABC. I mean, if the vector
Go to
is
the origin.
comma C, then the line
Say
passing
that again.
through. If the vector is A comma B comma C, then
Yes.
line passing through 0, 0, 0 and ABC represents that vector, right?
Of course, suppose you are given a vector. Now, can you find a line passing through 0, 0? Does there exist a unique line? So the
A
question
unique
is,
line, yes, of course, because from given 2 points, we can draw only one line to it.
you don't have, you are not given a point actually, right?
It's we,
You are given a direction, a
oh,
point and a
so
direction.
the given point is ABC, right?
No, I've just given a vector, arbitrary vector.
Yes, the vector, let's call the vector ABC, that is the head of the vector is ABC.
No, head of the vector. I mean, yeah. I mean, it can be arbitrary.
Yes, so it's ABC, any arbitrary ABC. So we draw the line passing through 0, 0, 0 and ABC. That is the line that represents that vector.
What is that line?
X minus A by
Given,
A equal to Y minus B by B equal to Z minus A by Z.
don't think too much.
T
Of
into
course,
V,
this is. But
where T is a
what is that
parameter.
line? Huh?
TV,
Yeah. Can you give a parametric form of it
yeah,
in
T
terms
is the
of t?
parameter.
What is the parameter?
T into V. Oh, the parameter is T.
Right. So given a vector v, there exists a unique line. So this is not. There exists a unique line passing through the origin. That is actually this is Vt.
Oh,
T is enough.
okay. Okay.
Right? Simple. So this is the map looking at v t goes to Vt, and now so this one. So now if you want to look at this form, it's nothing but it is bringing T naught first to the origin, and then looking at the direction, looking at the vector along this direction, right? And then whatever you got, we shift it there back. So is it clear? So bringing first this point to the origin, which is actually t minus t naught, right? So if suppose t naught is just the origin, right? T naught is, if t naught were just the origin, then you would have gamma prime t naught times t, right? And it will be gamma 0. So this is the line. This is the line passing through T naught. Well, this is the line passing through this whole thing, line passing through gamma T naught. And what is this? This is the line passing through the origin, right? At t equal to T naught, it is 0. At t equal to T naught, it is 0. So you have this vector, and at T naught, it passed through origin. At T naught, it passed through origin. If you look at the vector, the line here, this line corresponding to vector gamma prime T naught. And this line, which is here, which is this one, got shifted back by gamma t naught, and this is a dot. Right. So this is how you actually get the tangent line. Uh, so the point is you don't use slope now, but yeah, it's something called direction, either direction cosines or direction ratios. Yeah, but it is the easiest way to look at is this one. Just 1 minute. Sorry for this. All right. So any more question here? So this is one very simple representation, simple-minded representation of the derivative of a curve gamma. So you've got a tangent line as well uh, in this way, and of course you can get it in terms of your equation, favorite equation in 3D geometry, and you can get direction cosines and direction ratios, and you can check which one is this one. Right. All right. So let us look at few examples. So example, let's look at the following: gamma t equal to t comma t square comma e to the power t. Right, and you can definitely well you can actually definitely calculate what is gamma prime at any point. So if you look at gamma prime is 0 is just 1 0 and 1. So right, so how do you get this one? If we try to draw this, what would be the curve of this? So t comma t square actually gets a parabola, let's say xy axis, right? And at each t you have uh, t comma t square is just so what is it, like this, right? Is it correct? T comma t square, first of all, so this is if you look at in xy axis, and at each, so this is the projection in the xy axis. So at each point you have exponential at each t, so exponential 0, it starts from 1, and this is, suppose this part is negative, so it is, yeah, something like this maybe. Yeah, I'm not entirely sure. So you got towards this, and then it would increase. Yeah, it would increase as exponential, right? So it would increase as exponential, but on this curve. So you what we have is this is the xy axis, and over there you have the exponential. That is, yeah, it goes actually this way. So yeah, it's difficult to draw at this point. I mean, I don't know how to draw, but it's actually on this curve. On this curve, it actually varies exponentially. So if this is positive, so it goes, as x goes positive, it increases. So it goes to exponential on z axis. Yeah. Anyway, so if,
Sir, just a small
yes.
thing. Like, is it okay to say that the curve that this set of points t square e to the power t will generate is
Mhm.
what you get when you draw e to the power x on a plane and then you fold the plane in the form of a parabola?
Yeah. So what do you mean by holding this plane in term in?
Folding this plane, like you have this plane, like let's say just a plane segment, not the whole plane.
Mhm.
Like it's a flexible segment, and you just bend it so that the plane forms a what is it called? It's not a parabola. It's called, like, if you take a parabola and you lift it out of the plane, the thing you get, it's not what do you call it? Like the
Yeah.
shape
So
you,
so it's not bending the plane because it is what you get. It is a curve, right? It is not a surface. So
yeah. So
bending.
the structure that the curve takes on that plane. That's what I meant.
Well, the curve will not be in a plane actually. So curve will not be in a plane. So if you, yeah, if you bend the plane as a parabola, uh,
Like you draw
well, yeah,
draw
let
exponential in
me
the xz
explain.
plane,
No, yeah, you need to draw exponential in xz plane, of course.
and then bend the xz plane in the form of this structure that you get when you just take a parabola and lift it out of the plane. So like any segment of it is a parabola, any parallel segment of it is a parabola. The structure that this exponential graph takes on the plane, that's the curve that we want. I mean, is it okay to say this?
Mm, yeah, actually, yeah, it looks like, but I'm not actually exactly sure if you see. The point is, for each t, you have the second component as t square, which actually parabola when you project it down to xy plane, right? The curve. So you need to check whether you really get that projection out there. You don't need to actually bend the whole plane. Of course, I mean it might happen that uh, yeah, this exponential curve in xz, yeah, it is exponential curve in the xz plane. So maybe I should draw that first, as you mentioned. So it uh, looks like exponential in xz plane, and when you project it to xy plane, what you get is a parabola, right? So yeah, so this is in xz plane. It is actually the, so if you look at just projection on the xz plane, it is the exponential graph, the graph of the exponential. So well, yeah. Now in the second coordinate, yeah. uh, so this is the exponential, and, Yeah, I think you might be true, but I'm not exactly sure. So this part one need to see in a software maybe what you're trying to say. Maybe you to try to find a better argument to see this that one, but I'm not clear at this moment. So this is example one. Yeah. So
Sir,
this is
sir, uh,
yes.
sir, could you just go back up to the tangent part? And I didn't quite get why we have t minus t naught as the.
So you don't quite get this one t minus t naught.
Yeah.
So t minus t naught is this. So what is this? This one, right? So you need to think T naught to be origin, right? You need to think T naught to be origin, and this is the line here for this one.
So
Okay.
is it that given the vector gamma prime t naught, we want to draw a unique line through t naught?
True. We want to draw a unique line through T naught, and how to do it?
Vt, so gamma prime t naught times. Okay, you shifted up. You shift the.
Uh, Shift the origin to minus or T naught to the origin first, and then look at this one, this TV part. What I said this one, and then shift that back to gamma t naught. Shift that back to gamma t naught, right? That's what it did. So this one, adding this one, actually shifting that the whole thing back to gamma t naught,
Okay. Okay. So got it.
and this one is shifting t naught to origin in the beginning.
So first we shift from the origin to t naught, and then from t naught to gamma t naught.
Oh no! From t naught to origin. See, at t equal to t naught, it is zero. So this part is actually shifting t naught to the origin.
Okay, so we shift
So
from
look
t
at
naught to
this.
the origin and then back to gamma t naught.
Right. So you'd shift T naught to the origin and do whatever you want to do, and then shift it back to
Okay,
gamma T.
okay, okay. Got it.
That's how we got this. Right. And of course you can passing through. Yeah, and that is how you do. Because this is what is the simplest way to look at a line along a vector and passing through origin, and so this is what we use here. All right. So let's look at more examples. Yeah, so yeah, maybe you can actually try to look at this one in the software. Let me try this GeoGebra. If you use. So what do you want is
Sir, I have an idea, sir.
yeah. Tell me.
Sir, first we take projection onto XZ plane, sir.
Yeah.
Okay, then we'll get two-dimensional picture of that. Then we'll take that as x comma y. Then x comma y goes to x square.
Hmm.
X
X
comma y
comma
goes to
y
x
no.
square.
Right. Right.
Then
Right.
t comma e power t, we'll take that t comma e power t curve and map it to t square.
Hmm. Right. 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 That is true. So, but this is let me try to see. Let us try in a different way as well. So sorry. is x square. So this is x comma y comma z. X comma y comma z equal to x square. Then power x. Does it give anything? Should have given. I don't know.
So this looks like the projection on XZ plane.
That is true. Yeah, that is true. This is just yeah. So what? Right. Yeah.
Maybe intersection of y equals to x square and z equal to e power x.
Yeah. So yeah, I tried using three function levels. So yeah, the graph of three functions. So it is actually going into 4D. That is a problem. All right. So yeah, I understand what is the problem. So let us. No, this doesn't work. Yeah, say that again. What is your idea? X equal to?
Y equals to x square and z equal to e power x.
Yeah.
These two graphs.
True. This should work. Yes. Y equal to x square. Yeah. See. And z equal to right e power x. And this it gives the same thing, is it? Oh no, this I made mistake. So z equal to e power x. X. This one, let me erase this. What is happening? There's some problem. So this one I should remove. This one also. Z equal to e power x. Yeah. What's going on? Hmm. Do you see the intersection? Doesn't see the. It looks like the intersection, right?
Sir, I also
This
tried GeoGebra. In my case, it was showing intersection and both graph simultaneously.
you got this?
Yes, sir.
Okay.
Sir, Sometimes GeoGebra has some problems. Like, can you just close this tab, open GeoGebra in another tab, and try again? I think it will work. Sometimes GeoGebra does these type of things.
Um, yeah, let us try this. So y equal to x square, right? Then add 1. Z equal to e power x. Yeah. Now you see the intersection?
Yes, sir. It does look like an e to the power x drawn on the parabola taken out. What I was saying.
Yeah. That is true, but I mean, hmm. No, the point is you. So if you bend the plane like parabola, it's just this plane, right? This parabolic stuff. So what your thing was a little complicated. You draw a exponential graph first, and then bend it like parabola, right? So that was little more complicated to think of, right? So you right. So and then of course, yeah. I mean, bending the whole plane like parabola. You see here, you are looking at just exponential x. You are looking at just exponential graph first, and you are actually intersecting with the parabola, right? So this should be the correct way to think. So you are looking at intersection of two surfaces, uh, right? So these things are surfaces, and of course, I mean, bending thing, it might work, but it's not entirely visible. So you need an argument. So maybe try with an argument that it's really drawing that one and bending like a parabola. Yeah, possibly it possibly would work, might work.
Sir, we can take x comma y goes to x square and take domain as x comma e power x.
Yeah, that is true. That is true. But what he was saying is bending that plane like parabola. So he's not just bending this one, bending the whole plane like parabola. So yeah, it might work. It might work. Yeah, right. Anyway, so this looks good, right? So this one you think a little more, that whether the bending whole plane, we are doing the same thing, intersecting this one and bending that. Okay. Anyway, let's go back here. Let us try another example too. So consider this function gamma t is equal to cos t comma sin t comma t. So what is it? So cos t comma sin t gives you a circle, right? Yeah. Anybody saying something? So if you look at xz plane, xy plane, that is always a in circle. The projection is circle. So if we look at the following, this is x-axis, this is y-axis, and this is z-axis. So on the projection along xy plane is just circle, right? So it is actually it is within the cylinder. So it is within this cylinder. So what would be the curve? It would be actually it will start at t equal to 0. It will start from 1, right? So this is let's 1 comma 0 comma 0, start from 1, and then it start moving. Starts moving something like this. Does it look good? So similarly here, yeah. Actually, the last part is a problem. It should be parallel. So this is called helix. So this is not the part of the curve. This is not part of the curve. This is just I mean it's inside a cylinder. It is actually it's inside a cylinder, right? So now if you look at the point 1, so which 1 comma 0 comma 0, this is there. So gamma of 0 is 1 comma 0 comma 0. So what is gamma prime 0? Yeah, 0 comma 1 comma 1, right? Right. So what is the tangent direction would be? X equal to 0, and this um, at yz it's just 1 comma 1. So this is something like this. It is something like this here. Yeah. Does it make sense? Yeah. So you can look at the picture in GeoAlgebra or any other app if you like. Okay, let's go back to the definition of derivative. So now what we have is the definition. Let us recall the definition. Let us recall the definition of differentiable function, differentiable map from the f from, let's say, u subset of Rn to Rm, right? So, so what was we said? F is differentiable at A in U if there exists a linear transformation lambda from Rn to Rm such that limit h tends to 0, h belongs to Rn, f of a plus h minus fa minus lambda h is norm by norm of h is equal to 0. Right? Now, can you give an example of differentiable map? So, first example we should take. So, suppose t from Rn to Rm, a linear transformation. Right? So, you have seen linear transformation in linear algebra course, right? Yeah. So, is linear transformation differentiable? Yeah, the question is linear transformation differentiable?
I think yes.
What will be its derivative?
Seems like yes.
I, it
At a
should
point,
be
let's
t
say 0,
itself.
a itself, right? So, f here, so definition continues, f is differentiable on u if f is said to be, if f is differentiable at every point in u. All right. So yeah, so this is very simple, right? You want to look at t of a plus h. Let's look at a in Rn, and this you want to look at t of a plus h. So what is the linearity property? Yeah,
T of A plus T of H.
t of a plus th. So this implies t of a plus h minus ta is equal to th. So yeah, let me write one more step. T of a plus h minus ta minus th is equal to 0. So this implies norm of t of a plus h minus ta minus th by norm h. So h tends to 0. Limit h tends to 0 is 0, right? So this implies lambda is equal to t, right? So its notation. So here, yeah, before going further, let me here put notation. So the derivative of a function of a map, let's say, f from U to Rn, U is subset of Rn, is denoted uh, at a point. At a point A in U is denoted by df at A. Alright? So here dt at A is lambda for all, sorry, for this is t for all A in Rn. Right, so this is t is the linear transformation, this works. So
Sir,
have you seen? Yeah.
is there any intuitive explanation why a linear transformation behaves like the exponential function? Like given the derivative is the same as the function?
So this is the interpretation of the derivative, right? So you want to get, what do you want to get? You want to get a linear transformation, right? Lambda, right? You want to get a linear
Yes.
transformation, and you want to approximate this part by linear transformation, right? Let
No,
us look at this limit carefully.
that's all right. Like when we were studying functions in from R to R, then we know
Hmm.
that the only set of functions which satisfy dt equal to t or df equal to x, let's say, are the functions of the form k to the power x.
Right.
But here, all linear transformations are satisfying that property. So why is a linear transformation behaving like an exponential function? Is there any, I mean, any connection between these two? A
Yeah,
linear
why is it so? So what do you? How do you think that it behaves like exponential function?
like it satisfies this very special property of like after differentiating you are getting it's giving back the same function, right?
Yeah, that is true. But why does this? Where does this exponential comes from?
In R2R, only functions which satisfy this property are the exponential functions.
No, no. So your question is, so suppose f is from R to R such that f of x plus y is fx plus fy, right? Right. And then what
Hmm.
kind of function you have?
I think the only functions which will satisfy this property is the exponential function.
Exponential will not satisfy this one.
Oh, okay. No, if x equal to kx will satisfy.
Right. So this, you see, this one, perhaps you don't even need continuity, but you can assume continuity.
Hmm.
Suppose this was such that this one, then fx has to be ax
But if you
for all x
differentiate fx, then you get a, right?
for, for some a in right. Yeah. So if you take derivative, this is an interesting question. So if you take derivative, f prime x, which is just a, right?
Hmm. So f prime x is not equal to fx.
Of course it is, right? As a linear transformation. What is a linear transformation? What is the derivative? Remember what we did, how we constructed linear transformation last time out of taking derivative. So your derivative at x at a point x is a. That is true. That is true, but it corresponds to the linear transformation h goes to ah.
Oh, okay. That's
So this is the linear transformation you actually have
okay.
at every point, at every point for this case. So in general, so we had this f from R to R, a function, a differentiable function function, then f prime a is a number, right? It belongs to R. That's why you can do this. I mean, because you can do it this quotient, limit quotient stuff, and you get a number. But this actually corresponds to a linear transformation. H goes to f prime a h. So it changes as you change a. As you change a, this linear transformation gets changed. Right? So this is the linear transformation.
Yes, sir.
And here, for the linear, if you start with the linear transformation, then the same linear transformation would work. Same linear transformation would work actually as lambda. So it is actually the derivative. So if you look at this, your real analysis derivatives in terms of this limit, you will see this should be t will be replaced by f prime a h. All right. So is this clear? So use of linear transformation here. The question was existence of a linear transformation, right? Existence of a linear transformation. How do you find existence of a linear transformation, right? That's the question we should deal with. For linear map, yeah. Well, it is very easy just by inspection that the T works. But what about general function, right? What happens for a general function? General map from Rn to Rm. How do you find this linear transformation? So an exercise is the exercise. Suppose f is differentiable, so f from Rn to Rm is differentiable at, let's say, a in Rn, then show that the following one is f is continuous at a. Secondly, there exists a unique lambda from a unique linear transformation t or lambda from Rn to Rm such that the limit h tends to 0, which is in Rn, f of a plus h minus fa minus lambda h by h is equal to 0. Right. So existence of linear transformation gives you the differentiability, right? Which is already assumed. You need to show the uniqueness. This is the part you need to show. That this is unique, right? You just try to use triangle inequality, and suppose you have 2, then you look, let's say lambda and mu are 2, then you look at the difference lambda h minus mu h, and then use this addition subtraction stuff, this one, and then triangle inequality to get it. Okay, so try this one. This is an interesting exercise. So once it exists, it must be unique. So once we prove this one, then if we find a candidate, then it should be the one. So here, see, this is the notation. The derivative of a map. The notion of the derivative of a map will be well defined, provided this linear transformation it has to be unique. So linear transformation is unique. Otherwise, this notion of derivative will not make sense. You see my point? Yeah? Is this clear?
Yes.
Okay, so anybody who is not clear about this thing? Yeah, so this must be understood. So everybody should understand this one properly. So we'll actually look at more examples. So once we clear the stuff, we look at its interpretation and other things. But until everybody clears up these things, we will not proceed further. So we'll do some exercises. We'll do some more examples along these lines to understand the linear transformation. So, but this is a very important question, the uniqueness. So please try to do it. Think of it at least. Okay. Yeah. All right. So I'll stop here.
Sir,
Yes.
sir, I just wanted to inform you that I have mailed you regarding the timing of the food in campus. So it has been changed to